Hey everybody. So today we're going to learn something called the Dual Simplex method. So 2 lessons ago we learned to write duals, and we learned a little bit about them. We solved a primal and a dual, and we saw how they related. Last lesson we looked at all those relationships and all the powerful stuff you can do to use these duals. Now there's one other thing I want to show you. There's actually a whole lot more math out there that uses the duals, but I wanted to show you something really simple and that'll be pretty useful to us called the Dual Simplex method. Okay. Now I do want to say this is the last thing we'll cover in this section before we take a test. So I'm looking at giving you a test on Friday. Okay. I'll email you all the details about how this is going to work. That test on Friday. What I'll do is I'll email you the test, and then I'll send you some details on how I want you to submit it to me. I'll give you until Monday, Monday morning, so you might as well turn it in before Sunday night. Okay. I'll give you until then to turn it in. So, I'll give you more details on that. It'll cover all the last little bit of stuff we've been going over since our last test. Things like sensitivity analysis and the two-phase and big M and unrestricted and signed variables and duals and dual simplexes, which I'm fixing to go over today. Okay? And I'll give you a lot more detail on that in an email to come sometime soon. I'll also give you a homework. I'll send that to you. Actually, if you're watching this, you probably have already gotten the homework. I'm going to send it right after doing this, and I want that due on Friday, and then I'll give you the answer key on Friday. Okay. Awesome. So now let's get to this dual simplex method, and let's talk about what it is. So use a little bit of imagination with me here, and let's imagine that you have I'll make something up. Let's imagine that you have a simplex table, and all the reduced cost, it doesn't matter how big it is, all the reduced costs are non-negative. Well, let's actually make one of these be basic. So anything like this. Okay. So nothing is attractive. So you kind of feel like you're at the optimal, but you're not, because we're infeasible. Okay, so imagine this with me. I don't care what's in here, but there's no attractives. And you are primal infeasible. Okay, so this is not a situation we sit in quite often. Maybe if you had one that had no attractive variables and required a two-phase or big M, but just kind of ignoring that for a second. Let's just say that you're sitting right here with infeasible variables and no attractive variables to pivot on. Now, consider this for a second. If you were to write the dual for this problem, these would switch places, right? The dual would have two variables and a lot of constraints, but the dual would be sitting at something like this, 0, 2, at this same corresponding pivot to the primal. The dual would be sitting here. Now notice that the dual would be feasible, and it would have attractive variables to pivot on. Do you see that? Because the dual would just turn this sideways, right? These reduced costs would become the right-hand side, and these right-hand sides would become the reduced cost. And so we would be feasible. We would have attractive things to pivot on. And so that brings about this idea for the dual simplex method. Okay? It's actually kind of going to be like doing the simplex pivot on its side. All right? So here's the idea. We're going to use these things in the primal. We're not going to write the dual. We're going to just do dual pivots with the primal simplex table. We're going to say, hey, this is infeasible, let's do a pivot. Hey, this is infeasible, let's do a pivot. And let's make sure that we don't push anything into attractiveness. So at some point, we'll hit feasibility in the primal. We're already feasible in the dual, and we're not going to mess that up. Well, then we would be at an optimal. Would be feasible with no attractives. So that's kind of how this is going to work. We're going to pivot until we are primal feasible. All right. Now, I will say this thing is used for a few things in particular. Actually, it's strongly tied into sensitivity analysis. This is used a lot, like if you're finding a new optimal after adding a constraint, or finding a new optimal after changing a right-hand side, and if it's not feasible, or just solving normal minimization problems without having to do anything too fancy. And so that's kind of one thing I wanted to look at. That's the example I'm going to do. Is we're going to go with min x1 plus 2x2 subject to, let's see, and our constraints are going to be x1 minus 2x2 plus x3 is greater than or equal to 4, and 2x1 plus x2 minus x3 is greater than or equal to 6. And of course, all the variables are non-negative. So if we put this in a simplex table, x1, x2, x3, I'm going to need a slack or an excess variable for each constraint. Okay. And let's see. And so I have 1, negative 1, 0, negative 1, 0, 4, 2, 1, negative 1, 0, negative 1, 6. Because these are greater than or equal to, remember we're subtracting off the slack, so negative 1's there. But I can pivot to make these the variable that is in the basis. And then let's put the cost. Now remember, with minimization problems, we turn them into maximizing the opposite. So maximizing negative 1x. And up here goes the opposite sign. So positive 1x and positive 2 and 0, 0, 0. Okay, and we're going to say we're at 0. And so we say, hi, I don't have any starting solution. That's no big deal, though. Let's multiply this by negative 1 and this one by negative 1. And, oh, maybe I can, well, nah, we won't be that lazy. I can write this over again. I was going to copy it. Huh. Right hand side. Let's see. This is not changing any. Now, we do have a variable with a 0 reduced cost that's not going to be basic. So we may have to worry about alternate optimals. Whoops, I'm multiplying by negative, so this is going to become positive 0, positive 1, 0, negative 4. And this is going to be slack 1. Okay. Multiply by negative, so 2, negative 1, negative 1, oh, positive 1. I keep doing that. Positive 1, 0, positive 1, negative 6. Alright, so let's see where we're at. We're at an objective function value of 0, and we're at the point x1, x2, and x3 are non-basic, so they're all at zeros. But our slack 1 is at negative 4, and our slack 2 is at negative 6. So we're infeasible right now. Okay, that's not good. So this is where the dual simplex comes in, okay? What we're going to do is we're going to look here and say, okay, well, which one of these is most infeasible? Okay, which one's most infeasible? That's going to be our attractive one to pivot on. So this one right here is most infeasible. Okay? And we're going to look down throughout here. Now, this is going to feel backwards. Usually, we only pivoted on positive entries, right? But with the dual simplex method, we're looking to get rid of this negative, so I'm only looking to pivot on negative entries. So I'm only going to look at the -2 and the -1. And what's cool about this is we do in fact have a ratio test, but it's different. We're not looking back towards the right hand side. We got to compare this ratio to the cost right above it, okay? So the ratio test this time is the reduced cost divided by the entry, okay? And we always choose the smallest in absolute value. We're ignoring the signs. We're always going to choose the smallest, okay? Oops, I forgot the rest of my M, smallest. Choose smallest, and that's where we're going to pivot. So we already know how to pivot. This is just how we're going to choose what to pivot on. So most attractive is slack 2 because it's the most most out of feasibility. And then let's check the ratios. So the ratios, it'll be reduced cost over the entry. So 1/2. So this ratio is, I'll write it directly below it, is 1/2. This ratio is 2/1, or 2, ignoring negatives or positives. And these are positive entries, so I'm not going to look at them. So either of these, which one has the smallest ratio? Ding, ding, ding. So x1 is going to enter. Slack 2 is going to leave the basis. So there's where I'm going to pivot. So let me perform the pivot. Change colors again. So let's see, x1, x2, x3, slack 1, slack 2, and the right hand side. So if I perform this pivot, I'm going to want to get this to be a +1. So I'm going to multiply through this entire bottom row by -0.5. So if I do that, I will get +1, +0.5, -0.5, 0, -0.5, and +3. And instead of slack 2, we are pivoting in x1. Okay. Now I'm going to need to zero out the row above it and zero out its reduced cost. Okay. So if I'm using these values, all I have to do is add these new values to the row above it, and it will zero out this -1. So let's see. So 1 plus that -1 is 0. 1/2 plus 1 is 3/2. -0.5 plus 0 is -0.5. 0 plus 1 is 1. -0.5 plus 0 is -0.5. And 3 plus -4 is -1. Oh, we almost pushed it all the way to feasibility right there, but didn't quite make it. Slack 1 is still infeasible. Alright, now I'm going to need to zero out the reduced cost, which is not going to be too difficult because this new one is a 1. I want to zero out a +1, so multiply this new row by -1 and add up to the last cost. So that this one, -1 plus 1 is 0. -0.5 plus 2 is going to be 3/2. Double check by math. -0.5 times negative is +0.5 plus 0 is going to be +0.5. 0 added up to 0 is still 0. And negative of -0.5 is +0.5. Added to 0 is +0.5. And we're going to add up there -3. Awesome. Okay, now look at where we're at. We're at our right-hand side. Our objective function value is at 3. Remember, it's opposite signed. Okay? And the point I'm at, x1 is now at a value of 3. x2 and x3 are still non-basic. Slack 1 is at -1, and slack 2 is non-basic at 0. So nothing became attractive as far as the normal simplex goes. Okay, so this is actually dual feasibility right here. We are dual feasible. But in the primal, we pushed one more variable feasible. I still have one infeasible, okay? So we're going to do another dual simplex pivot because we're not all the way feasible yet. So let's look at slack 1. It's the only attractive one we're doing dual simplex pivots. We're only going to look at negative signs. Okay, so either this one or this one. We got to do our ratio test. Oh, that's really interesting ratio. 1 half divided by 1 half is 1. 1 half divided by 1 half is 1. So you could literally pick either of these. I'm going to go what's called lexicographically to choose the tiebreaker here, which means the one that's farther to the left. Usually it's the lower index, and if we thought of these as x's, this would be like x4 and x5. So I'm going to pivot on this one since there's a tie. If there's a tie, you could choose either. I cheated, though. I know that's the best one to choose because that'll finish the problem for me, and I'll be optimal. Well, remember what did I tell you? You might have to watch out for alternate optimal solutions, but we'll see what we end up with. We might not have to worry too much about that. Okay. And so, S1 will leave, X3 will enter. And so we're just going to do one more pivot, and hopefully we'll be done. We'll be dual feasible, we'll be primal feasible. There should be no attractive variables because we're following, I forgot the R, right hand side. We're following our ratio test, so we shouldn't push anything too far. Okay, so let's see. I'm going to need to get this to be a positive 1. So I'm going to multiply through by negative, not 2. Negative 2 should give me to positive 1 right there. So let's see, that'll be 0, negative 3, positive 1, negative 2, positive 1, negative 2 is what I said, right? Negative 2 times, but all right, and that is now going to be x3, right? Awesome. I'm going to use the old row to zero out below and above because it's pretty easy to zero out the reduced cost here. So I just need to add it up, right? So that'll give me 0 plus 0 is 0. 3 halves plus 3 halves is 6 halves, which is what, 3? Negative a half plus positive a half is 0. My zeros were kind of hurting a little bit there. Let's see, where was I at? 1 plus 0 is 1. Negative a half plus a half is 0. Make sure I did that right. Negative a half, okay. And negative 1 plus negative 3 is negative 4. Okay, awesome. Now we need to zero out below. Okay, so to zero out below, we're going to, let me double check that I did not copy something incorrectly here. I was looking at my worksheet. Where is this? X3. We have these and just add. Okay, we're good. Never mind. Looking at the wrong problem. Trying to confuse myself here. Alright, where was that? I lost where I was at. Okay, so now we need to zero out below. So just multiply through by negative 1 and add it down. So 0 plus 1 is 1. Negative 3 halves plus 1 half. What's that going to give us? Just negative 1. 1 half plus negative a half is 0. Okay, things are going well so far. I'm at this one now, right? Slack 1. So we're multiplying by negative and adding down. So this would be negative 1. Cool. And multiplying by negative and adding down, that is 0. Multiplying by negative and adding down, so this pushes to 4. And this is x1. So look at where we're at. Our objective function value is at 4. The point we're at, x1 and x3 are 4 and 2. So 4. x2 is non-basic. x3 is at 2. And the slacks are non-basic. Okay? Now look at where we're at. Nothing else is attractive, so we're optimal. Nothing is infeasible, everything's feasible, so we are at the optimal solution. Okay? Which is awesome. That makes me thrilled. Alright, so that's a dual simplex. Now, it's pretty neat. It's just basically doing the simplex pivot sideways when we have infeasibility. And it's actually pretty awesome for these minimization problems with greater than or equal to constraints, because the only other way to do these would be big M or two-phase to get a feasible starting solution, because you start infeasible. Now I will say, because nothing is attractive, that does kind of help us with that sum. All right, so let's see. Yeah, sorry, I was double checking the solution. Something felt sketchy for a second. For 8 minutes. Okay, awesome. So that is the solution. I do want to point out something else. Notice I have a non-basic variable that is at a reduced cost of 0. So there might be alternate optimals. So you could pivot and explore that if you wanted to, but I'll leave that to you. I forgot to write optimals, alternate optimals. But otherwise, that's all we're gonna do today. Okay. Well, have an awesome day.